Forest fire can be considered either a threat to forest resources, property, and public safety, or an important ecological process, depending on when and where it occurs. Fire managers need to be able to make instant evaluations of fire danger in a rapidly changing environment in order to plan effective operations. Fire danger rating systems have been developed to provide useful and timely information on fuel flammability and potential fire behavior from a wide variety of fuels, weather, and topography data. In Canada, the Canadian Forest Fire Danger Rating System is used by all agencies as a principal source of fire intelligence. It is one of the few fire danger rating systems that is fully implemented throughout an entire country. The Canadian Forest Fire Danger Rating System is composed of 4 subsystems that reflect different aspects of fire danger. They are the Fire Weather Index System, the Fire Behavior Prediction System, the Fire Occurrence Prediction System, and the Accessory Fuel Moisture System. The Fire Weather Index System is the cornerstone. The purpose of the FWI system is to evaluate how flammable the forest is at any time, because as the weather changes, fuel flammability and fire danger change too. It is important to understand how the system works in order to use it effectively. The Fire Weather Index System has a modular design. It is composed of 3 moisture codes: the Fine Fuel Moisture Code, the Duff Moisture Code, and the Drought Code, and 3 indexes of fire behavior: the Initial Spread Index, the Buildup Index, and the Fire Weather Index. Each of these values can be used on its own, or they can be combined to produce the Fire Weather Index, which rates fire intensity in a standard forest type. The codes and indexes were designed to provide the maximum amount of fire danger information from the minimum amount of daily weather data. In this program, we'll look at the basics of the FWI system, how the FWI system is constructed, what kinds of forest fuels are represented, how fuel moisture changes, how the FWI codes and indexes work, and how to calculate the values. And we will assume a basic knowledge of fire weather and fire behavior. Forests contain a variety of fuels: crown fuels, live and dead understory vegetation, downed woody debris, and forest floor organic matter. The FWI system tracks the moisture content of 3 different types of forest floor that have different drying rates: litter, loosely compacted duff, and deep compact organic layers. These fuels are thought to be most critical to fire behavior in temperate and boreal forests. Fires ignite more easily, spread more quickly, and burn more intensely in dry fuels because it takes less energy to heat them to the point of ignition and combustion. The moisture content of forest fuels is affected by weather elements such as rainfall, temperature, relative humidity, and wind speed, and so it varies over the fire season. Typically, there are several drying periods lasting from a few days to a few weeks and separated by rain events that recharge fuel moisture. What we need to find out is how much the fuel moisture content changes each day. During drying periods, fuels lose moisture at a rate that varies with weather and the kind of fuel. Starting at the saturated moisture content, fuels lose less moisture during each successive hour or day in constant conditions. If conditions remain constant, the fuel moisture content will eventually reach equilibrium with the relative humidity of the atmosphere. At this point, the fuels have lost all of their available moisture. The length of time it takes for fuels to lose 2/3 of the available moisture between any point and the equilibrium level is called the time lag constant. During wet periods, fuel moisture increases. The amount of wetting that occurs varies depending on the type of fuel, the amount of rain, the existing moisture content, and how much rain is intercepted by the forest canopy or by other fuels. Fine fuels can also absorb moisture directly from the atmosphere, depending on their moisture content and on relative humidity. The 3 moisture codes are, in effect, bookkeeping systems that simulate the amount of daily wetting and drying of forest fuels over the fire season. Each fuel moisture code has a wetting phase, the effects of rain on increasing fuel moisture, and a drying phase, that evaluates the amount of moisture that is removed by that day's drying influences. This daily procedure works as a memory so that each moisture code calculation reflects the impact of both past and current weather on fuel moisture status. All three moisture codes are constructed so that higher numbers represent drier fuels.
The first of three moisture codes is the Fine Fuel Moisture Code, or FFMC. It's a numerical rating of the moisture content of the surface litter layer 1 or 2 centimeters in depth.
The FFMC scale is 0 to 101. Because it represents the moisture content of fine fuels where most fires ignite, FFMC is closely related to ease of ignition. Fires won't start in most fine fuels until the moisture content is below about 25 to 30%, or above FFMC 78. The FFMC is sensitive to daily temperature, relative humidity, wind speed, and rainfall. It only takes about a millimeter of rain to raise the moisture content of fine fuels above the ignition threshold. However, FFMC fuels also dry quickly. If we start at the saturated state, about 250% moisture content, fine fuels will lose 2/3 of their available moisture in about 2/3 of a day under standard conditions of 21 degrees Celsius temperature, 45% relative humidity, and a 13 km/h wind at noon in July. If you follow the FFMC through several days with these same conditions, you will find that after 3 to 5 days, the code levels off. There is essentially no more moisture to lose, and the fine fuels are in equilibrium with the atmosphere. This means that the FFMC has an effective memory of a few days. Of course, higher temperatures and wind speeds and lower humidities can all hasten the fuel drying rate and reduce the equilibrium moisture content. The lowest moisture content seen in fine fuels is about 2%. An important feature of the standard FFMC is a built-in prediction of the daily peak fire danger conditions. Fine fuel moisture varies during the day with a wave-like pattern in response to changing temperature and humidity. It is usually lowest in the afternoon around 1600 hours and highest before dawn. Though the standard FFMC is calculated from noon weather readings, it represents the fine fuel moisture content around the critical time of 1600 hours. However, an hourly FFMC can be calculated from hourly weather readings, and a diurnally adjusted FFMC can be estimated for any hour of the day from standard daily variation in temperature and humidity. If they are available, these more specific values should be used for predicting the behavior of individual fires. FFMC can also be adjusted for slope and aspect effects in some situations.
Now let's look at the Duff Moisture Code, or DMC. It's a numerical rating of the dryness of the forest floor layer 5 to 10 centimeters deep. It corresponds to the F, or fermentation layer.
The flammability of the duff layer is important because duff consumption is the main source of the energy produced by the moving flame front in forest fires. The DMC is related to fuel consumption in moderately compact duff layers and medium-sized woody fuel. The weather factors involved in DMC calculation are daily rainfall, temperature, and humidity. The DMC scale doesn't have an upper limit, although the duff has lost all available moisture by about DMC 200. The duff layer holds about 15 millimeters of water when it is fully saturated, at which time it has a moisture content of about 300%. In many fuel types, the duff starts to be involved in combustion when the DMC is about 20. DMC fuels dry more slowly and have a longer memory than fine fuels. If we start with saturated duff, it takes about 15 standard drying days to remove 2/3 of the water. That leaves a moisture content of 115%, at which time DMC would be about 45. If no rain fell for 70 days, The duff would continue drying to its equilibrium level of about 20%, and the DMC would be around 200. Of course, each time rain falls, a wetting factor is applied, which decreases the code value. Then the drying process starts again. The amount of drying that occurs also varies with day length. This is accounted for in the DMC by applying a monthly drying factor. For example, a day in June has almost twice as much drying power as a day in September with the same standard noon weather conditions.
The third moisture code of the FWI system is a long-term drought indicator. The drought code, or DC, is a numerical rating of the moisture content of deep, compact organic layers 10 to 20 centimeters thick.
The deep duff is not usually consumed in a moving fire front, and so doesn't contribute to frontal fire intensity. However, smoldering combustion can occur in deep organic layers following lightning ignition or the passage of a flame front. The DC is an indicator of seasonal drought effect on forest fuels, total fuel consumption, and smoldering in deep organic layers and large fallen logs. Drought code, or DC, is driven by the daily rainfall, noon temperature, and month. Deep organic layers can hold up to 100 millimeters of water, which results in a moisture content of 400%. The DC scale, like the DMC, doesn't have an upper limit, but the deep duff has lost most of its available moisture by about DC 800. Deep duff dries slowly by a process known as evapotranspiration and has a lag time of 53 days. When fully saturated, it takes 65 standard drying days to reach 100% moisture content, or a DC of 500, which is about the minimum required to support smoldering combustion in deep duff. Compared to the DMC and FFMC, the DC has a very long memory. At most times during the fire season, the forest floor is usually drier at the surface and wetter with depth. However, when light rains follow a period of drought, as often occurs in the early fall, a moisture reversal can occur, where the deep duff is drier than the surface. Because of its long memory, the DC will continue to indicate the smoldering potential. Occasionally, overwinter precipitation in some areas falls short of the 200 millimeters of water required to recharge the deep, heavy fuels represented by drought code. Where recharging of the deep duff layers has not occurred, the drought effect can be carried over to the next year by adjusting the DC starting values in the following spring. The three fire behavior indexes of the FWI system are numerical ratings of relative fire behavior in a standard jack pine or lodgepole pine forest. They can be correlated with fire behavior in other fuel types using mathematical models or from personal experience. Like the moisture codes, higher index values reflect more severe fire behavior. The ISI, or Initial Spread Index, is a numerical rating indicating relative spread of fire immediately after ignition. It combines wind speed with fine fuel moisture, as reflected by FFMC, and can be updated at any time as the wind speed changes. ISI increases exponentially with wind speed and doubles with every increase of 13 kilometers per hour. Wind speed increases with height above the ground and is much greater in forest openings than within forest stands. A standard wind speed, measured at a height of 10 meters in the open, is used in the ISI calculation. Although it's called an initial spread index, experience has shown that the ISI is well correlated with spread rates in all sizes of fires across many fuel types, and so is a key variable used to predict rate of spread in the fire behavior prediction system. The fifth component of the FWI system, the Buildup Index, or BUI, provides a numerical rating of the amount of fuel available for combustion. BUI is a weighted combination of DMC and DC without any additional weather elements. The two moisture codes are combined in such a way that the upper duff layers, represented by DMC, really control the BUI. Long-term drought effect is given a small but variable effect. For instance, if DMC is 0, indicating saturated surface fuels, BUI is also 0, no matter how high the DC. However, when DMC is greater than 0, the DC effect increases the value of the BUI above the DMC value. The maximum possible effect of the DC is to raise the BUI to a level that is double the DMC. Because the DC tends to rise over the summer, BUI is usually higher in the summer than in the spring, even for the same DMC. The sixth and final component is the Fire Weather Index itself. The FWI combines the BUI and ISI into one numerical rating of fire intensity, where the BUI represents fuel consumption and the ISI represents rate of spread. The individual BUI and ISI values indicate the relative importance of fuel consumption or rate of spread to overall fire intensity on that day. For example, a BUI of 200 and an ISI of 5 gives an FWI of 24. The same fire intensity occurs with BUI 24 and ISI 18. However, it is important to be aware that much higher spread rates are involved in the second case, although fuel consumption would actually be less. It may also be significant whether the ISI in the second case resulted from a high wind and a moderate FFMC or from a low wind but very dry fine fuels. FWI has been scaled as a fire danger index dependent only on weather inputs in order to give uniform results in FWI values in temperate and boreal forests. The FWI is related to fire intensity and fire behavior characteristics in the standard jack pine or lodgepole pine forest. The FWI is only used by itself for the broadest of planning activities when a single number is needed. FWI alone or in association with BUI is generally the most effective way to describe classes of fire danger. Many fire management agencies have developed fire danger classes to guide broad-based fire management activities such as prevention, preparedness, and detection. Fire danger classes are based on the relationship between past fire activity and the Fire Weather Index system components. This graph shows the relationship between FWI and fire danger classes over one season in southeastern British Columbia. The FWI can also be transformed into a severity rating that can be used to compare average fire weather conditions between months, fire seasons, or locations. Now let's review the weather readings that are required to use the FWI system. They are air temperature, relative humidity, 10-minute average wind speed, and rainfall accumulated over the previous 24 hours. All of the weather readings have to be taken at 1200 local standard time in order to calculate the standard daily values. In addition, hourly temperature, humidity, wind speed, and rain readings are needed to calculate an hourly FFMC and ISI. The month is also needed to account for the effect of day length on drying rates of DMC and DC. At the beginning of the fire season, the FWI system calculations are started up for a weather station using standard values that reflect saturated conditions. The weather readings should begin after the snow leaves the ground. A continuous daily weather record is essential. Missing data need to be estimated. If a station is started up later in the season, then it is important to make a good estimate of the starting DMC and DC for that site. This is because the startup values can have a significant effect on DC for a long time and a noticeable effect on DMC until the code is reduced to 0 by the first heavy rains. The starting FFMC value is less critical because it will have little effect on FFMC after a few days. Weather stations should be located in large openings with a diameter of at least 10 times the height of surrounding trees in a representative area away from water bodies, roads, and buildings. The anemometer height should be 10 meters above open level ground, and temperature and humidity should be determined in a standard shelter or radiation shield. Instruments should also be checked periodically throughout the fire season. It is very important that weather observations used to calculate FWI system values follow these standard procedures to ensure accuracy, because the system has a memory and errors can accumulate. The FWI system values can be calculated in one of two ways. The standard method is a set of mathematical equations processed by a computer program. Approximate calculations can also be made using printed tables. The daily standard FWI system values, calculated from noon weather observations, represent the mid-afternoon peak of fire danger conditions. Other programs and procedures can be used to adjust FFMC values to other times of day, or to calculate FFMC around the clock from hourly weather data. This also allows for the adjustment of ISI and FWI. Because the FWI system is based on weather, forecasted weather values can also be used to forecast the codes and indexes on an hourly or daily basis. The daily FWI system values are a good way to synthesize a collection of weather readings into a few indicators of flammability. This allows comparisons of relative fire danger over wide areas and over the course of the fire season. It is impossible to capture a complete picture of fire potential in one number. Each of the Fire Weather Index System components provides an important piece of fire danger information. A better understanding of the FWI system enables managers to use it more effectively.